our final exam review for mechanics of materials. The next topic we need to cover is bending stress. In our chapter on bending stress, we were dealing with beams, and once we've identified the internal bending moment somewhere, we need to be able to calculate that stress. So our bending stress equation is my over I, where m is our internal bending moment. If we are bending about this axis, then we would be measuring y as the distance up or down away from that centroidal axis. And so what we end up getting, if you look on the side of that beam at the end, is if here is our centroid, this bending moment, I like to think of it as that arrowhead is pushing in on the bottom. So we end up with compression at the bottom for the way I've drawn my bending moment on this picture. And then on the other side of the beam at the top, we'll end up with tension. And at the centroid, so it's also called the neutral axis, goes through the centroid, and it's called neutral because there is no bending stress right there. And our moment of inertia, if it's just a rectangle, we just look it up, 1/12 BH cubed will work fine for any rectangle. We find the moment of inertia about the centroidal axis of our cross section, and then we measure how far away from that we are to figure out our stress. And then it's up to us to figure out, are we in tension? In this case, tension is up at the top is positive, or compression down at the bottom is negative. So if we want to find where our stress is max on the cross section, that's going to be at our extreme values. So max at the top or the bottom, whichever is farther from the centroid. And by max, I'm meaning absolute value max. So it could be a max tension or max compression. So for a rectangle, your peak tensile stress and your peak compressive stress will be the same, because in a rectangle, it's the same distance to the top as the bottom. But for a shape like a T, we would end up with a centroid that is not in the middle. And so you'll notice that we have a much smaller distance to the top than we do to the bottom. And so our peak stress would be, in this case, down at the bottom. It's wherever you have to go to get the very farthest from your centroid. And the bending stress will always be 0 at the centroid, also called the neutral axis. I sometimes have students get a little bit confused by these pictures. We have one picture that indicates the beam itself. So this is something that's very long, very slender, and it has loads applied to it. In this case, somebody's cut it open and found out what the internal bending moment is right here where we care about it. Well, then we need to look at the cross section. That has to do with how tall is the beam, how wide is it into the page, what shape is it. So we'll often be accompanied by a second picture over here, which is if I were to cut the beam open and turn it and look at that end, what shape do I see as I cut it open at a section? And we usually draw that much larger because this base and this height are small distances measured in either inches or millimeters versus the length of the beam that might have been measured in feet or meters. And similarly, this T shape is an alternative kind of cross section you might see if you cut open the beam. So you'll oftentimes with these problems see both a beam and a cross section. They are related to each other. One's looking at the side, the other one's looking at the end. Next, we have transverse shear stress. The equation that we use for transverse shear stress is that transverse shear stress tau is equal to VQ over IT. So if I've cut it open and I've found my internal shear force, that goes right there in the top of the equation. And I want to remind you, we do not use tau equals V over area. That's a very poor approximation. It assumes the stress is uniform, and turns out the stress is not uniform. So if you have a fairly large cross section, you want to use this more accurate equation, tau equals VQ over IT. Well, how that works is let me zoom in on my cross section, kind of draw it in 3D. What it turns out is that the shear stress is going to act in the same direction as your applied shear force. So if that's downward, this is going to act downward. And it's going to be max in the middle and decreasing as you go out toward the edges. And it's actually 0 at the top and bottom. And that distribution is actually parabolic. So this is a parabolic stress distribution. So in terms of max, it is max at the centroid, and it is 0 at the top or the bottom. Let's see what goes in here. V goes in the top. Moment of inertia is the moment of inertia for the cross section. So if it's a rectangle, you're just going to plug in I equals 1/12 BH cubed. And the thickness, that would be the thickness measured perpendicular to the force. So if the force is in this direction, you go perpendicular to it. And this would be our thickness. So thickness would be equal to B if it's a rectangle. And the thing that's tricky to find is Q. We'll spend a little bit of time reminding us what Q is equal to. Q is called the first area moment, units of inches cubed or meters cubed. And the idea behind Q is if I want to know the stress right here and the shear force is vertical, I want to take a cut or draw a line that goes like it's drawn here right through the point where I want to know the stress and perpendicular to V. And then you're going to shade everything on one side of that line. And that area right there that we just shaded is A prime. The first area moment, Q, is equal to A prime times something called Y bar prime. So A prime is an area. It's the area of everything above or everything below that line that we just drew, which is through the point where I want to know the stress. If my shear force were in a different direction, then I would draw my line perpendicular to the shear force right through the point where I want to know the stress, and I would shade everything on one side or the other. That would then become my A prime. So it's always the area one side or the other relative to the point where you want to know the stress. Y bar prime is the distance between the centroid of the whole shape and the centroid of A prime. So we need two centroids. Centroid of the whole shape, maybe you want centroid of the whole shape red. Centroid of the whole shape is red. It might be right in the middle. And then I also need to find the centroid of my A prime. Maybe make it green. So the middle of that hash marked area. And if I can find that distance between those two guys right there, that'd be my Y bar prime. And over here, that'd be my Y bar prime. I guess in this other one, it would technically be called Z bar prime because we've changed coordinate systems, but it's just a distance between the two centroids. So centroid of your whole shape and centroid of your shaded area. And that's how we're able to figure out the stress at different locations, right? This would be for finding the stress at this purple dot location. If I wanted to know the stress over here at this end, I would use a different A prime and a different Y bar prime or Z bar prime. We now know all the different kinds of stresses that we're interested in. We know how to find the stress from normal forces, shear forces, bending moments, and torques. So we're going to put it all together in our chapter on combined loading. So first up is two-dimensional. And we usually do this for beam-like structures. So the idea with the two-dimensional beam structure is I'm going to cut it open somewhere and find the internal loads already drawn on here. We'll have a V, an N, and an M, and those are the only three you have in 2D. So to solve for the internal stresses, we simply need to find this normal stress, which will be a combination of the stress from the normal force and the stress from the bending moment. And I put plus or minuses on here because then we go look at the picture to figure out at the location we're interested in, will they be added together or subtracted, and will the result be positive or negative? And for shear, we simply need to use a single VQ over IT equation to find the shear. It'll be in the same direction as our drawn shear force. And then what we'll do is draw on a little representative volume element the result. So our shear stress, we said, was going to go down on this right edge. So it's got to go down on the right edge. That wouldn't be an equilibrium. So we have to draw a countering upward one. That's still not an equilibrium. That would start rotating. So we have to draw another pair on the top and bottom edges just for equilibrium purposes. So you should, when you're done, you should have these guys head to head and tail to tail all the way around. And now for normal stress, it depends on where we're at. If we're at the bottom of the beam, this bending moment is drawn so that it would be pulling in tension at the bottom of the beam. So at the bottom of the beam, our bending stress and our stress from our normal force would both be positive, and we would end up with a positive stress. If we were at a different place on that cross section, we might get a different answer. If we're in the middle of the beam, Y is 0, and our bending stress goes to 0, and we would only have the normal stress from the normal force. And if we're at the top of the beam, it'll switch to negative because we're in compression at the top, and maybe that will be the biggest, and we'd actually end up with a compressive stress. So there's a little more work to be done than just writing the equations and finding this. You do need to know exactly where on the cross section you are. I mentioned the bottom and the top. Well, if you're at the bottom of the cross section, tau is actually 0. Because remember, tau is a parabolic distribution. It's max in the middle and 0 at the top and bottom. So let's look at one in a little bit of detail. What if we wanted to find the stress state at point D right here? So our solution process would be, number one, draw a free body diagram before you start cutting anything open to find your reaction forces. So in this case, I would probably draw a free body diagram of bar AB, because then I could find the reaction forces at A. And I've noticed that BC is a 2-force member. Free body diagram of beam or bar AB. And then we are going to use equilibrium equations to solve for AX, AY, the force in BC using equilibrium equations. Then, only then, are we going to cut it open at D and draw a little free body diagram of D. That would look something like this is cut open. We would have an AY and an AX that we solved for already. And then at our cut, we would have a normal force, a shear force, and a bending moment. And I'm not quite done. We also need to include just the part of the distributed load that acts on the little section that we've kept. So just that triangle. So we cut open at D and draw another free body diagram. You are not getting out of this final exam without drawing some free body diagram. What do we do with the free body diagram? We're going to solve for V, N, and M, our internal shear force, internal normal force, internal bending moment. Now, once we've found those, we can actually go and grab shear stress and normal stress. Normal stress is going to be plus or minus N over A, plus or minus My over I. And our shear stress would be V, Q over IT. Mentioned about Q, they've given us a detailed drawing of our section showing us that point D is 20 millimeters from the top. So that's going to be important information, both for figuring out what to plug in for Y in our bending stress and for figuring out Q. So for our bending stress, this Y, let me draw that just a little bit bigger. Point D is right here, and we've got 20 millimeters to the top, and we've got a centroid down here somewhere. It looks like it's going to be another 30 millimeters down, right? Because this overall thing is 100 millimeters tall. So half of the height's 50. So if you go up 30, you'll get to D. So the Y is going to be 30 millimeters when we find our bending stress. So we got to start at the centroid and go up to point D. Now for Q, our shear force is acting in a downward direction. So you want to draw a line right through point D. It's perpendicular to your shear force, and shade one side of it. So when you do that, Q, which is A prime Y bar prime, the A prime will be 20 millimeters times, looks like it's 50 millimeters wide. And then the Y bar prime has got to be the distance between the centroid of the whole shape right there and the centroid of the shaded area. So we already had to go 30 millimeters to get from the centroid to D, and then we got to go another halfway up. The whole thing is 20, so we got to go another 10 millimeters to get to that red dot. So the two red dots are 40 millimeters apart. So here is our A prime, here is our Y bar prime. At point D, we would figure out, depending on the direction of M and N, whether they add or subtract at that point, whether the overall stress is positive or negative. Let's do 3D. The rest of this is just about 3D combined loads. So I'm going to start with a case where somebody has already done the work of finding the internal loads for us. And then on the next example, we'll do the work where we have to actually find the internal loads ourselves. So if we already know the internal loads, what I like to do is break them up into each of the different loads and figure out what the stresses are that each of those cause at the point I care about. So we can potentially in 3 dimensions have 6. We could potentially have a normal force in the X, VZ, VY. We could have a torque, and we could have bending moments about both the Z and the Y axis. This example I grabbed from the textbook has 5 of those. It has a normal force, or 500-pound normal force. It also has a shear force in the vertical direction, but there is no shear force in this direction. The shear force is the 800 pounds downward. Let me write that one down. And then we have a torsional moment. The torque is right here. You know, it's a torque because the axis goes down the middle of the shaft, and it's a moment about that direction. So the torque is 11,200 pound-inches. That's this one. And then the other two are both bending. So this 7,000 pound-inch, it's a moment about the vertical axis, moment about that Z-axis, and it looks like we're going to be bending that way, right? Where our thumb is pointed up, so we're going from A that way. And that one is 7,000 pound-inches, and that's this one. And then finally, the other bending moment is this 8,000. Again, thumb pointed in the direction of the arrowhead. It looks like it's going from the top to the bottom. So that one is going to line up with this other bending moment here. This is the 8,000 pound-inch one. So let's talk about what each of those do. The normal force, 500 pounds. Normal force causes nice uniform stress like they show right here. So it doesn't matter if we're looking at the stress at points A, B, or C. It's all going to be N over A, which in this case comes out to be 0.283 KSI in tension. For the next one, we're dealing with bending. Bending caused by this 7,000 pound-inch moment, which is going to pull out at A and push in on the back side. So this moment, if we were looking at points C and B, it'll cause no stress because they're on the neutral axis, but it will cause a big amount of tension at point A. So that's what they've figured out right here. It's going to cause tension at point A, compression on the back, and no stress along that vertical axis. Gives us a tensile stress using the equation sigma equals my over I. And the y distance that you use is from the axis, the moment's axis out to point A. So it actually be equal to your radius. And then shear force next. The shear force is pointed straight down, 800 pounds. So you'll remember shear stress is maximum at the middle and 0 at the top and bottom. So it's going to be maximum at A. And that's what this picture is supposed to show, is a big stress in the middle. And they calculated that using our friend tau equals VQ over IT. Calculated that stress to be 0.604 KSI. Now that next bending moment, the 8,000, that's this one. We're bending about this axis. And in doing so, with that positive bending moment this way, we're basically pulling on the top, pushing on the bottom. So it's going to cause tension up here, compression down there. Is that what the picture shows? Yep, tension up here, compression down there, and no stress at either A or C. So if we were looking at point B, we'd have compression. But since we're looking at point A, we actually get no stress from that one at point A. And then torsion. So our torque is this way. Put your thumb in the direction of this arrowhead and see which way your right hand curls. And so you'll remember torque causes stress that changes direction as we work our way around the circle. So with the torque going this way, we're going to have a downward stress at point A, which is what the picture shows, a downward stress. And that comes from our equation, tau equals T rho over J, polar moment of inertia, and rho is your radius. When we put this all together to put it on a picture, I like to kind of draw a little cube to indicate that I understand how these stresses are going to combine. Normal stress, let's start with that. I've got in the positive direction 0.283 and another 21.13. So I'm going to end up with a normal stress like that. And it's going to equal to 0.283 KSI plus 21.13 KSI. So my two normal stresses will add up because they're both tensile. And then for shear, let's look at the shear. I have this shear is causing me to go downward at point A, 0.604, and this shear is also causing downward at point A, 16.9. So my shear stress on that front face that I'm looking right at is going to be down here, downward. I'll end up with tau equals 0.604 plus 16.90, and it's all in KSI. And it's not a good idea to leave that shear stress all by itself. Remember that the shears are always going to have tail to tail, head to head, friends, to keep it in equilibrium. And I don't usually bother drawing the arrows on the back side because the picture just gets really cluttered if I try to. Let's do a full one. Full example. So let's say they haven't given us the internal loads and we actually have to do the work to find them. I'm going to show you my shortcut of how I get these the easiest way for me. If we want to know the stress right here, we've got to cut it open right there and draw a free body diagram. The free body diagram would look like this guy over here, right? You've got your applied loads applied. And now you would need to find that, oh, if that's got 300 going that way, we got to have a 300 opposing it going that way. And if we've got a 500 going that way, we would need a 500 going that way. Now, I don't actually like using the free body diagram for purposes of doing three-dimensional internal loads. And here's why. It's because that face right there is actually hidden from view. So here's a little shortcut. Instead of drawing, I mean, we can go ahead and draw it on here as well. Instead of drawing everything equal and opposite, we have a downward 200 Newton. So we'll have an upward 200 Newton so that when we sum forces in the what I'm calling the y direction, they all add up to 0. Well, look, when I cut something open and I draw both sides of the cut, this upward force will have to have an equal and opposite pair on this other face that is pointed exactly downward, 200 Newtons. So a little shortcut is, instead of drawing 200 down, 200 up, and then 200 down, you can just directly put your 200 Newton load right there. Because if you're pushing down on the structure here, you're also pushing down on that face there. And the same thing with the others. We had an applied 300 that way, so we can draw a 300 in the opposite direction, but then on the opposing face, it would be in this direction, 300 Newtons. And the same with the 500. On our free body diagram, the 500 would need to be opposite, but now if we put it on this other face, it's opposite again, and opposite and opposite is where you started with. So we have the forces done. This will be in force equilibrium, but not moment equilibrium. So we've got to figure out moments as well. And here's how I think this is easiest. I like to go back to my original picture and figure out what is the moment that these three forces cause about the X, Y, and Z axes right where my cut is. And then I'm going to draw them right on this face. So we'll find the moment these cause about that location, draw them here, and you'll know you'll have to have the opposite moment here for this guy to be in equilibrium. Let's start with the x-axis. The 500 Newton force causes no moment about the x-axis because it lines right up with the x-axis. The 200 Newton force causes no moment about the x-axis because it lines right up with the x-axis. But the 300 Newton force does cause a moment. It's going to be that way, which is a positive moment. My thumb would be pointed out in the positive x direction, and its distance away is 2 meters. So I end up with, in the x direction, and I'm going to draw it way out here so it doesn't get too cluttered. There is my moment about the x-axis, happens to be a torque or moment about the x-axis, and it's equal to 300 newtons times 2 meters. And if you want to draw the opposite of that back on your free body diagram, torque about the x equals 600 Newton meters. Let's do the next axis. That next axis is the y-axis. So about the y-axis, the 200 newtons causes no moment because it's parallel to that axis. The 500 newtons causes no moment because its line of action is lined right up with that axis. But the 300 will cause a moment about the y-axis, and it is 1 meter away from that axis. So 300 newtons times 1 meter, and it looks like that is going to cause a negative moment about the y-axis. So I'm going to draw it that way. It'll be a 300 Newton meter my. And if you want to draw that over here, if that's a -1, so if that moment is going like that with my thumb pointing down, my moment on my other face would need to go the opposite direction with my thumb pointing up. And using right-hand rule, it would be moment about the y-axis like that, which should counter the moment that would be caused about the y-axis by my 300 Newton force. So we just want the arrowheads to be pointed opposite directions, right? The 500 is going that way, so the 500 is going that way. The X torque is going that way, so on this face it has to go that way. This is going downward here, so on this face it would go upward. We're not actually going to use this diagram when we're done, but I want it to be right. And so we have one axis left. We have the z-axis, and the 300 newtons is parallel to the z-axis and will not cause a moment, but the 200 will cause a negative moment. It's 1 meter away, and the 500 will also cause a negative moment 2 meters away. So altogether, about my z-axis, I'm going to end up with a moment about the negative z-axis, and it's going to have in magnitude the 200 newtons times 1 meter plus 500 newtons times 2 meters. And if you want to draw it on the other diagram, if that one's pointed back in the negative z direction, you would want this to come in the positive z direction, and there's your mz. We have all of our internal loads now, so now we can do what we did with that previous problem. And what I want to figure out is not the numbers, but just the process for a circle that has points A, B, C, and D at 4 different points around that circle in the 4 different quadrants. Let's first work with the normal force. And I've grouped these where these 3 are the things that will cause normal stresses. Bending moments and normal forces cause normal stresses. So let's deal with all of those first. Normal stress caused by normal forces, it's uniform over the entire cross section. And I am drawing it in tension. I should probably double check that it actually is in tension. Yes, it is. My 500 newtons is tensile force, and so I'm going to end up with a positive normal stress from that. I just need to divide it by the area, so you would end up getting N over A, N over A, N over A, and N over A. It doesn't matter if you're at A, B, C, or D, you will have that stress added in. Now let's look at bending about the y-axis. The y-axis is this vertical axis right here, and there is my bending moment, and it goes in that direction, thumb pointed downward, right hand. So we're coming from the back to the front. So our arrowhead is on the front face, coming away from the back. So whatever axis you're bending about, you will have no stress on that axis. So we've got no stress on the y-axis. Our tension side is back on the back side, and compression on the front, or tension at D, compression at A. So let's try to draw that. on a sketch. There is our axis where we have no stress. Out here on the back face, we're going to have tension, we said. And here on the front face, we're going to have compression. They're going to meet in the middle, sort of. It's a linear distribution. Looks something like that, if you want to try to sketch what the stress does across there. So at points B and C, this does not contribute at all, but at points A and D, it does. At point A, over here, we're in compression. So I'd want to put a minus M. And now I need the distance from my axis to the point, which in this case is actually the radius, over the moment of inertia of the shape. And which moment am I putting in here? This is the moment about the y-axis, because we're bending about the y-axis. Now what about point D? At point D, I would want to add, same thing, moment about the y-axis times r over I. And I don't add anything to sigma B and sigma C because point B is right up here and point C is right down there, and they are on the bending axis. It's the neutral axis, so there is no stress caused by that bending moment. Now the Z is going to be a different story. The bending about Z is this moment. It's negative, thumb toward the negative Z axis. So that is going to pull on the top and push on the bottom with no stress on the Z axis. So there's my Y axis. Here is my Z axis where there is no stress. And what did I just say? Tension at the top, compression at the bottom. So we're going to have tension and compression, and those are going to go down to 0 at the middle. Something like that. So tension on the top, compression on the bottom, 0 at the middle. So at point B, I said I have tension. So I'm going to add at point B, moment about the Z axis times how far we are from the Z axis, which is R, over I. And then at the bottom, at point C, we'll have minus mz r over I. So for every one of those points, we're actually only adding up or subtracting 2 stresses, because one of the bending moments contributed no stress at each of those points. And I've got a little note over here that I comment to myself that when we go to plot these on the little boxes in a minute on the representative volume elements, I'm going to assume that the bending stress is way bigger than the normal stress caused by the normal force, because it usually is. So when I subtract these two, I'm going to assume that I'm going to get a negative number because this guy is bigger when we plot those. But we got to do shear stress next. So these three, the 2 shear forces and the torsion, will cause shear stress. Let's look at our Y shear force. The Y shear force is this downward 200 Newton force. So what that's going to do is, if the force is downward, you want to draw a line perpendicular to that, and along that line in the middle is where your stress is big, and then your stress gets littler as you go toward the top and bottom. And it's 0 at the actual top and bottom, 0. The top and bottom here are B and C. So this stress will not contribute at B and C, but it will contribute at A and D. So at A and D, I'm going to have my V in the Y direction times Q over IT, and the thickness at that point is going to be 2 times the radius, because that's how thick it is right there. And at D, same thing. I'm going to have VYQ over I times 2 times the radius. As far as the sign goes, I'm just going to say that these are going to act, for now, I'm just going to make a little note to myself that these act downward. Next up, we've got Z shear force. That was this 300 newtons, and it's acting in the positive Z direction that way. So let's kind of draw a little reminder. It's acting, pointing in that direction. So you draw a line perpendicular to it, and your shears are going to go in that direction, big in the middle and smaller as you get toward the edge. So it's going to be 0 right there and 0 right there. It's going to be 0 for A and D. So we won't add anything to A or D, but it's going to be max at B and C. Plus 0, plus 0. And this guy, I guess I could have put zeros there, plus VZQ over I. And again, the thickness will be double the radius. Here we get VZQ over I times double the radius, with a little reminder that we're going to be pointing to the left, because that's the direction our shear force pointed. And then finally, we have torsion. Our torque was a positive torque right here. So if I like to just kind of draw the torque on here, if the torque is going that way, it means that my shear stresses are going to go around the circle kind of like so. At point B at the top, the shear is going to the left. At point A, the shear is going down. At point C, it's going to the right. And at point D, it's going up. So I'm going to add to all of these. We're going to have TR over J, TR over J, TR over J, and a TR over J. Now let's see which direction they are to decide if it should add or subtract to what I already have on there. At point A, looks like it's going down. So this is down. At point B is at the top. It looks like it's going to the left at the top. Point C is at the bottom, and it's going to the right at the bottom, right? Yeah, going to the right at the bottom. So this would be going to the right. And then finally at point D, we're on the right, and it looks like it's going up. So we're going up. Okay, let's figure out if we're going to add these. So in that first row, this guy was going down, and this is also going down. So these are going to sum. And in the second row, they're both going left. Shear is going left, and the torque is going left. So they're also going to sum. Now this next one, they're in different directions. The one from the torsion is going to the right. The one from VZ is going left. And my note here that I'm going to use is that the shear stress from torsion is usually larger than the shear stress from shear. So I'm actually going to make that the governing positive one, and I'm going to call the other one a negative, so that when I'm done, I get a positive number, and I'm going to just use the torsion to figure out my direction. And then same thing with this last one. These are opposites, right? I got an up and a down. So I'm going to call the up one the positive because it's going to be bigger, I'm anticipating, and I'm going to make this guy a negative. So I only put those signs in there because I figured out that these are acting in opposite directions, and I wanted it to come out positive. Let's do the shear since I'm already on this page with shear. Tau A acts downward. B acts to the left. C, you've got a mix of right and left. I'm going to pick what I think is going to be bigger from the torque and right. And then D, I'm going to pick what I think is going to be bigger also from torsion and have it go upward. And then let's fill in the rest of this on the visible faces, head to head and tail to tail. And then let's just go figure out what our stress was going to be. So we end up with, I'm assuming the bending will be biggest. So we're going to end up with compression at A and compression at C with tension at B and D. So compression at A looks like that. A and C are compression, and B and D are tension. There's a little bit of variation in which stresses show up on which face, but this is a pretty typical pattern that you rarely would end up with a stress at a point that goes up and down and another one that goes side to side. They're usually both up and down or both side to side. They might add, they might subtract. And you will usually have some of your stress components that are zero at any given point. So if you were asked to solve this problem for point A, all you'd actually need to calculate are these two stresses, the stress caused by the shear in the Y and the stress from the torque. And up here, you'd only need to calculate the stress caused by the normal force and the one about the y-axis. You wouldn't actually need the one about the z-axis. That concludes our final exam review on combined loads.